Happy holidays, everyone. Hope your weekend is going well. We have three topics to take a look at for homework number 12. So the first one is going to be a look at what's called Green's theorem, uh, which we're going to use techniques for integration to find area. And then we'll look at two techniques for finding that involve the derivative for finding rates. So Green's theorem. What we use Green's theorem is that it gives us a relationship between line integrals definition. What we're working with, we've got some region that is bounded by a curve. One of the things we're going to look at is the orientation of that curve is always going to be going counterclockwise. So the positive orientation counterclockwise. If we go the other way clockwise, then that will give us a negative orientation. So the direction counterclockwise, and as long as it's a vector function with boundaries of a and b, then region D will always, as we can kind of see here, will be on the left-hand side of the curve as we take a particular point going through the curve in a counterclockwise orientation. So the positive counterclockwise. If we go the other direction, then that has a negative orientation. So Green's theorem basically just tells us, we were working with these earlier when we integrate some function dx plus another function q dy, that is equal to the double integral finding the area of the region of the partial of q with respect to x. So the part that was with the dy, we take its partial with respect to x, minus the partial with respect to y of p. So that's whatever function is in front of the dx, then we're going to take its partial derivative with respect to y. So remember, we're doing the opposite. Whatever's with dx, we take its partial with respect to y, and whatever is with the dy, we're taking the partial with respect to x, and it's the partial of x minus the partial of y. Okay. So here is an example that we're going to go ahead and work through together. So this is the part that's with the dx, this is the part that's with the dy, and we have C as a triangular curve consisting of these line segments 0, 0 to 0, 1, 1, 0 to 0, 1, and then 0, 1 to 0, 0. So let's just do a little sketch of what that looks like. 0, 0 to 1, 0 would be here. 1, 0, here's 1, 0 to 0, 1, so that's up here. I guess the line segment, right? We're going here. And we're going to go, I guess, with the counterclockwise orientation. 1, 0 to 0, 1, and then from 0, 1 back to 0, 0. So we get this triangle. So there's our region, and we need to integrate this. And so one way of doing this is doing a, let me show you the, it's enclosed, so D is a region enclosed by C, has a positive orientation, so we've gone through that. One thing we need to pick up on our boundaries is, of course, this bottom line is just a horizontal line. We could think of that's really just y equals 0. There's a vertical line here. This is x equals 1 as a coordinate. So then we have to find this equation here. This is a linear equation. It's a decreasing equation. I mean, if if you think of this line here going from 0, 1 to 1, 0, we could use algebra to find that. Again, you would find the slope using the 2 points. Okay, 0, 1 and 1, 0. Find the equation of the line that goes through, and we'll see it's y equals 1 minus, or y equals, 1 minus x. Okay, so as we set this up, we're going to remember what ends up happening is we're going to get a double integral. With the first part is going to be the partial, so we're going to call this part here q, this part here p. So the partial q with respect to x, so take this derivative with respect to x, derivative of x is 1, so all that's left is y, minus this first one, the partial of the first one with respect to y. Well, there is no y, so y is a constant, or well, x is a constant. There's no y, so when you take this derivative, you get 0. And the area is either dy dx or dx dy. We're going to see there's some advantage with doing the dy part first, since there is a y variable here, so that sort of makes sense, but also the limits. Y goes from 0 if we go this direction until 1 minus x. So the boundaries, the upper boundaries here is 1 minus x. And then x is going to go from 0 to 1. Now if we went the other way, we would have to solve this one for x. We could. Remember, we can do it in either order. So this will go from 0 to 1. So now we just need to integrate that, and that's really just y dy. So we've got the setup now. I think we'll do that on the next page. Okay, so I'm going to clear a little bit of this out. Leave the function. Okay, so we have this. Let's integrate. So y dy, so y, that becomes y squared over 2. And that's going to go from 0 to 1 minus x dx, which goes from 0 to 1. Plug in the lower end, you're going to get 0, so that doesn't matter. So really we just have 1 minus x squared over 2. So probably foiling this out would be provide the best for integrating. So foiling 1 minus x, you're going to get x squared, x times x. You're going to get a negative 2x, and then you'll get a plus 1. And everything's over 2, so we'll just move the 1/2 out front. 0 to 1. And now we integrate everything, so we get 1/2 x cubed over 3, that's that part. We integrate this part, we're going to get minus 2x squared over 2, so you'll see the 2's cancel, plus x. And that goes from 0 to 1. Again, when we plug in 0, everything disappears, so we just plug in the 1's. So that is going to give us 1/2 times 1/3. Remember that canceled, so that just becomes minus 1 plus 1. These cancel out, negative 1 plus 1, so you get 1/6 as our final answer. And that's what the textbook did, basically similar type thing. I guess, we didn't have to multiply it out. Just to me, it made more sense to go ahead and do that. Anyway, 1/6. Okay, so there's our example of using Green's theorem. Now, let me go ahead and clear that. Okay. The other thing, though, is sometimes we had something set up in the area, and it sometimes the double integral is easier to evaluate, but sometimes the line integral is easier to develop, so we could use it in both directions. The main thing we're looking for is if we know that p of x is equal to q of x equals to 0 on the curve, then we get that this part, the first part here with Green's theorem, is equal to the summation of the two, which is still equal to 0. So it doesn't really matter what p and q are in this region. So we can go both ways with Green's theorem. So that allows us to also use it to find areas. Okay, so here's using that reverse direction of Green's theorem. So since we know we're given the area, when we have the area of the integral, if it's 1 times dA, when we integrate this over any region, it gives us the area. Okay, so what we want to do is be able to choose the functions p and q so that their partials equal 1, because again, this is what Green's theorem is telling us. If we have this inside the integral, that's the application of Green's theorem. Okay, so there's several possibilities we have for this. We could say p of x is 0, right? So if you take that, that's 0, and then q of x would be x, and so when you take its partial, you get 1. 1 minus 0 is 1. We could let p of the function p of xy be negative y, so when you take its partial with respect to y, you get negative 1, a negative make it positive, q is 0, so we get a sum of 0. Lastly, we could have negative 1/2 y, 1/2 x. Again, if you do that, you get your partials. You get 1/2 minus negative 1/2, which is 1/2 plus 1/2, which gives you 1. So these would also be functions that make it work. Okay, so that gives us 3 different sort of formulas to work with now, and this is just building off of Green's theorem. Okay, so we could have some sort of constant here times x dy, and that would be that first one, right? Q is this, so this is x. Okay, we could have a minus, so they bring the minus out of y dx. Okay, that was that second one, and here's the third one where we have basically 1/2 x dy minus y dx. Okay, so those are the 3 different cases, and what those will do is those will give us these partials will be equal to 1, so we could use it in any case where we're finding area. And so one example here, I forgot to itemize it, but we'll just kind of talk through this. Find the area enclosed by this ellipse, and again, what we want to do is use, so the ellipse is going to be circular. It's going to be an area. We can use a parametric equation using our thoughts from polar coordinates, what we've done before, and then if we let t go from 0 to 2 pi, we go all the way around and we'll get the ellipse. And so when we use these formulas, so if x is a cosine t, when you square it, the a squares will cancel out and you get cosine squared, right? So then that gives us, when we plug this in for x, we're going to get cosine squared t. When we put b sine t in for y, the b squares cancel, so then we get sine squared of t, and that's a trig identity. Those are equal. Okay, but what we're going to do with this, so this is an appropriate substitution. What we're going to do with this is go back to the previous templates. We're going to use this one, 1/2 x dy y dx. Okay, so x dy y dx. So there it is, 1/2. And what is x? Well, we defined x to be a cosine t, so that's right there. And then what's dy? Well, dy is going to be b cosine t dt. So that's that substitution for these two parts here. Y, we take its, we just plug it in, right? Y is b sine, so that goes there, and then we dx is going to be a sine of t, but cosine is minus sine, so that's where the negative comes from, and then dt. So that's dx, and that goes there. And when we multiply these, we get a times b, we get cosine squared, and here we're going to get a negative, which makes, so this is cosine squared t dt. We could factor out the dt to the back if you'd like. This one we also get a times b, the negative make a positive, and you get a sine squared t. Factor the ab to the front because they're constants. The 2 is still out there. This is 1 dt. So when you integrate it, you get t going from 0 to 2 pi. Of course, at 0 it's 0, 2 pi it's 2 pi, so then it's ab over 2 times 2 pi. 2's cancel, pi ab. So that would be its area. So that's a sort of a reverse use of Green's theorem to find area. Okay, so that's our first concept for today. The next one is we're going to talk about curl and divergence. So curl will be the first one, and we use this word curl. These we're going to be looking at derivatives, so these are going to be rates, and they are things that can be applied to vector fields. So each operation resembles differentiation. One produces a vector field, whereas the other is a scalar field. So curl is going to give us a vector field. Divergence will give us a scalar field. Okay. So curl, and one of the reasons we use this name curl is it's associated with vector rotations, the rotation of vectors. So we start off with sort of if we do have a vector field, some function, right? The x, p, q, and r, the x part of the function, q part of the function, r part of the function. And then we can get the partial derivatives of p, q, and r all exist. As long as that's the case, then we define the curl to be these partials as this. And we're going to get some, and you'll see that this comes from the dot product that we did earlier, and we're going to set this up in a way that makes it a little easy to remember, right? Because this is the z and the y functions in this x area here. this is the x and the z part, right? And then this is the x and the y part in the z. So we're going to see this is tantamount to taking a dot product. We're going to invent something new. We'll just call it the del. So this is related to the gradients that we did before, gradient vectors. So it's really, yeah, it's just the partial of x, the y component's the partial of y, and the k component's the partial of z. Okay, and so we do come up with a way to remember this a little more clearly, of thinking that we did this earlier, taking a scalar function to produce a gradient function. Did I say dot product? I think it's cross product. Sorry, I'm thinking ahead. So we're going to use a cross product method here, not the dot product. Okay. And again, with the gradient, we ended up, that's really what it was. So we were using this delta. So the way we want to think about it is, if we take this product, sort of this gradient idea, cross it with the vector function that we have, right, p, q, and r, then we're going to get the function we wanted. So remember, for the x part, it's sort of, you do a cross. Let's just go to the next slide. I think they did it for us. Okay, so you're going to have the r crossed with the y, so there's that cross product there, and the q crossed with the z, right? So we go from top to bottom, minus the bottom to top, I think, crossing over, however you want to do it. So that's where the minus part comes in. For the j part, we're doing it with the x and the z, and so we have partial of x times r. Oh wait, this is the one someone had mentioned to us, that when we're crossing across this, is to think of this as a circle. So we're going from the k direction. So this crosses over to the p. So we always start here, right? So that's p partial of z, and then the r, again, thinking of it looping around behind r to z. That's the part that gets subtracted. Okay, so that's because if we're doing y, we go to the next one, and these guys are sort of circular. So if we think of it, ijk, you think of it going sort of circular like this. So when we're doing the j, we start here and we cross it with the I. So we're looping around. We get that portion. And then when we do the k part, again, we start here, so that's kind of looping around here. The I component is the first part, so we do partial of x crossed with the q minus p crossed with the y. Okay, so that's, and again, you can just have these formulas there, but that ties us right back to when we were doing cross product stuff. Okay. And that's what we call the curl. So we've got a function, and I guess in a sense you're taking this function crossed with its gradient, and the end result is still a vector. So we're starting with a vector, we're taking the partials, vector partials, and we still have a vector, but we've got a curl field that is involves a derivative, so it's giving us a sort of a rate of change. So let's so if we think of this, we can manufacture this, but it's really curl is a gradient crossed with the function, the vector function. That gives us this curl. Okay, so let's attempt this one, trying to find the curl of f if this is our function. And again, we could go back and just memorize that formula, but just for the I guess what we're going to do is we're going to find the curl crossed with f. So ways to kind of just do this out. So p is going to be xz, y is xyz, and z is minus y squared. Okay, and this will be the partial with respect to x. This is the partial with respect to y. This is the partial with respect to z. I guess I, j, k. So to get the curl f, we're going to start with the I component. Is going to be, this one's maybe the easiest one. I always think it's the partial of y, taking the partial of y with minus y squared. So I'm just going to do that as we do it. So the partial of y is going to be, remember, we're taking derivatives, negative 2y. And then we're going to subtract this function, the partial of z. Well, the partial of z is just 1, right? So that's xy, and this is the subtraction part, so it's just xy. So that's the first part, and then we're going to plus something with j. For j, remember we take k and I, so, and we go around, so we're going to take the partial of z of xz. So the derivative of z is 1, x is a constant, so that's just the x. And then we do the other way, so maybe this one looping around up to here. So we're taking the partial of x, but there's no x here. Y is just a constant, so that's a minus 0. Okay, so that's that part. And then we're going to plus some part for the k. And again, we're doing k, we're coming from the ij, so this is the cross part. So we're taking this derivative with respect, the partial with respect to x, derivative of x is 1, so we end up with yz. And then we're going to subtract off this xz, the partial of y. Well, xz doesn't have any y in there, so when you take its derivative with respect to y, it's just a constant, you get a minus 0. Okay, so let's see, what do we end up with? So we get the curl of f. I guess you could factor stuff, but you could just say minus, let's see, take the y out. Maybe take a minus y out. And that leaves x plus 2 I. This looks a little cleaner, I think. This is just x, j, and this will be yzk. So that should be our curl. So it looks like we matched up pretty good there. And then they do all the work here. Yeah, they did. Okay, minus, they took a minus y out. They did 2 plus x, x plus 2, however you want to do it. Middle one is just xj, and then yzk. So we match up their answer there. Again, just using sort of this mnemonic to remember how you're doing it. To me, it's actually better than trying to follow the formula. I don't know. It just doing things crosswise seems to make more sense to me. Okay, let's go ahead and clear this out, and then and if we have a function, if f is a function of three variables, and if they have continuous second order partial derivatives, then the curl of the gradient will be 0. So remember, because what's the gradient? You're taking you're crossing basically the gradient with another gradient is really what's kind of happening. So all we're doing is substituting that this vector field is a gradient, and so what it's telling us is as long as f is conservative, then the curl of the function will be equal to 0. Is really what we're saying. So is it conservative? So it really helps us to it doesn't necessarily prove. I mean, we can't necessarily use this to prove that it is conservative, but if we take the curl of f as not equal to 0, then we would at least know it's not conservative. Doesn't always work the other way. And that's what it's saying. The converse is not true. Just knowing that the curl is equal to 0 does not tell us it is conservative, because there could still be some problems. But if f is a vector field defined on all three space, and all the component functions have continuous partial derivatives, and the curl is equal to 0, then f is a conservative vector field. Okay, so notice it's not an if and only if. It is a one-way, as long as we know that the partials are that we have continuous partial derivatives, that the curl is equal to 0, then we can say that f is a continuous vector field. And again, we said this earlier, but that curl is associated with rotations, and that's really what we're looking at is it's the velocity of the field, the flow field, and that's where we use curl. So that leads us to our last concept for this set of homework, divergence. And for divergence, this is where we're going to use the dot product. Okay, so we're just going to define we've got some vector field, some function times I, j, and k is a vector field, and that the partials all exist, partials of x, partial of y, partial of z. Then we define that the divergence of f is simply the partial derivatives added together. So notice that the divergence of a vector field is defined, what we end up with is a scalar. It's a number. Notice this is no longer a vector. Once we have these, we could add them together and we get a value, no longer a vector, so there's no direction involved. And we can think of this also in terms of the gradient operation. When we did this little del, that we're taking the partial with respect to x, partial with respect to y, partial with respect to z, and then we're going to do a dot product with the function itself. Okay, so the divergence is the del operator dotted with the function. Okay, so now this looks similar to, I think it is the same one we were using previously. And we're just going to be asked to find the divergence of f. And again, this is a little bit easier. We don't need as much mnemonics we're going to take this first part and we're going to take its partial with respect to x. So the derivative of x is 1, z is just a constant, so we end up with z. Here we're going to take the partial with respect to y, so y, derivative of y is 1, x, z are constants, so they just kind of come along, so it's 1 times those. And then finally we're taking the derivative of this last part with respect to z. Okay, partial with respect to z. Well, y squared is just a constant, so this part is 0. And so our divergence of f is simply, I guess you could factor it, z 1 plus x. And if we knew what values for z and x, that would give us the divergence. So notice this is a number, it's a value, it's not a vector. And again, they do the same thing here. It's just z plus x times z. We could leave it that way. That's what they did. You're just taking the partial with respect to x for the first part, partial with respect for y to the middle part, the j component, and then the partial with respect to e for the k component. And that's divergence. We do get a theorem that given a function, a vector field, on 3, if p, q, and r have continuous second order partial derivatives, then the div of the curl of f is going to be 0. So, and again, the reason divergence is understood as a fluid flow, how things diverge. But we can use this that if we take the divergence of the curl of f, and so that's kind of, remember, a dot product of a cross product, because curl of f is a cross product, the div is a dot product, that it would be equal to 0. Okay. So the div is really the net rate of change with respect to time when we're dealing with fluids or gases. And it's this change of the mass of the fluid flowing from a particular point using its volume. So it measures the tendency of the fluid to diverge from a particular point. And so if it's equal to 0, it says it's not it's incompressible, meaning that it's not diverging, it's not moving. And then we could also compute the divergence of a gradient vector field. But we'll leave that one for later. So this should be enough to get you through the homework, homework number 12. So we've got Green's theorem, we've got the calculation of curl and the calculation of divergence. Have a wonderful rest of the Thanksgiving break, and we'll see you all again on Wednesday.